Well, good evening, everyone. Thank you for coming tonight. The August 25th monthly meeting of the Fort Wayne Astronomical Society. As almost everyone here knows, I'm Joe Novosel, Presidente of Fort Wayne Astronomical. In just a little bit, you'll hear from Michael Arata on the cosmic microwave background and what it means to us and all sorts of other interesting questions. So we've got that to look forward to. In addition to Mike, we're going to have a couple of presentations in the so-called show and tell segment. I did a presentation at the last meeting on something called small groups, and I want to redo that for a slightly wider audience at this point and have it at least recorded so that we can reference back to it, point people to it to find out what exactly is this. And then Laura is going to do a presentation, actually a request for membership to the membership on a moon observing group that she would like to start up. She is starting up. So we're going to hear about that, and how you join and get connected together will make a little bit more sense after I do my presentation. So let's see. No new members. So we can skip on from that to Fort Wayne Astronomical swag. I think you've been hearing a little bit about the swag and the ability to get swag and all of that. And it's actually finally open and available. The swag URL is in the eyepiece. And to show Russell, if we could show me again. See, okay, good. I ordered myself some coffee mugs. So I have examples of 3 of them. And this one, of course, is the fine logo that we have here. So it's real. The stuff is available. It took about a week for all 3 of them to get delivered. So Christmas is coming. Get out. Get some swag. Jim, anything to add to that? New product coming? What?
We're other than that, it's going good. I bought 2 T-shirts online for samples, and I purchased one myself, and the other one has got the Astro Wars logo on, which is kind of cool. I can hold that up. That one. Let's see. Here's the front side. Yeah. And then here's Astro Wars. It's got it's Fort Wayne Astronomical Society, but it's got behind it some very nice imaging by Geddes, I think. But anyways, you can pick your color, pretty much if you like black or white or whatever. And there's the standard T-shirt. There's about 3 different varieties of T-shirt logos at least.
Yes. So it's real. It's available. They deliver. They take your credit card. It's all ready to go. And so hopefully we'll get some interest in it. And as I said, the URL is in the eyepiece in the President's Letter section. We'll have to get that as permanently installed along with our other social media URLs on page 1. We'll have that for next month. So let's see. I wanted to say a few words on Chat and Chew from last month, just to show a few pictures. So I want to share. July we had a meeting that was going to be held at Jefferson Township Park. We had lots of events I thought that were going to be fun and entertaining. Unfortunately, the weather didn't cooperate. We had lots of rain in the area. It actually was supposed to storm, and it all went around us. So we had about 17 people that did show up, and man, did we eat well. It turns out that the pavilion is actually a really good place to eat. You see that in the upper left corner of the picture over here. We have some play area for the kids, swing sets here, and slides and things. So kids would have been entertained for a few minutes. We had good facilities for doing a Zoom call. We brought over the modem out of the observatory and we had a really good internet connection using the modem. And there's AC outlets all over the place. So that turned out really well. And had a lot of good conversation. And since few people showed up, we had a lot to eat. So it turned out to be really nice. There was a flea market set up. That was one of the things that we were talking about doing. We made one sale in the flea market, and so that contributed to our project fund. Thank you, Ed. And Bill and Jim did a great job cooking, and everything really turned out well. So next year we're gonna go ahead and do it again. I think we'll probably look for a drier month, like maybe August, and a month that doesn't have such a late start in terms of getting darker. So we'll see. We got a little ways to go before we have to make decisions on the next one. But I think JTP's pavilion really turns out to be a good place, well protected, and we can do all the events that we would like in addition to that. So I look forward to that for next year. So we can move on. Oops. I actually wanted to leave that share open. Neil, did you have anything you wanted to say about Pokagon or Obachi?
Okay. Pokagon, it was Laura, Russell, and myself. Good support from both the DNR staff and the Friends of Pokagon State Park. A lot of good questions and enthusiasm from the campers. We did not need mosquito spray with where we were set up. We ended up getting a strong waft of wood smoke that kept the bugs down. For Obachi, we had a low turnout for Friday night. It's a hit and miss over at Obachi, but we did the Perseid program, and Laura did an excellent job on that. Once again, good questions. I think we might have seen 2, maybe 3 at most Perseids, but we're able to answer a lot of astronomy questions. And on Saturday, while we were closed at Jefferson Township because of the steam show, we ended up having Gene and Larry joining us out there. It ended up threatening rain, but the rain went around us, kind of the story of the jet shoe. And we did kind of a round table and dealt with questions relating to several key constellations. And we had about 10 turnout for that. So we're looking at possibly returning back in October over at Obachi. It'll be a Friday night star party. And don't forget, we have our Deep Sky Star Party coming up on Friday. Weather's looking like it might be good. And then also Saturday morning, we'll be setting up over at the United Arts or Arts United program. Will be part of the STEAM section and could use some help, whether it be for an hour or 2. We're starting at 11 and ending about 6, passing out information about the Fort Wayne Astronomical Society. Also, I will need some operators for StarQuest. I don't think my back is going to survive setting up around 10 o'clock and leaving after 6:30, 7 o'clock at Arch United. So we'll be doing some telescope work. Laura will be talking about atmospheric optics, be mentioning the light pollution, and then like I said, we'll be passing out some information and star charts for the Fort Wayne Astronomical Society. So, any questions? Somebody?
Yeah, Neil, where is the Taste of Arts Festival going to be? What's the address?
I'm going to send out an email with the downtown maps that they have given to show us where we can park, where we can offload. So I will do that to all members. So if you would,
Okay.
either give me a text or give me an email back. That would be great.
Sounds like that will be interesting and could be fun. So we'll see what we can do on that 23rd. That's this coming weekend.
Yep.
So, okay. Yeah, are you seeing a share of the Pokagon pictures, by the way? It says I'm screen sharing, but I don't see it, and I don't see it up anywhere. Excuse me?
Yes, we do.
Yes.
We see it.
Oh, okay, because I see your picture and I don't see that. So I will
I'm
go
going
ahead
to
and stop
mute
sharing.
my mouth and it'll take me off the screen.
We had quite a few people at Pokagon, right? You had quite a good crowd come out. It was like 130 or something? 113. Yeah, so.
Estimate because it was dark.
Was it dark?
It was very dark.
Good.
Yeah.
Good.
I mean, there's no lights at that site.
I think that's a good reason to go up there, to actually experience a dark sky. We don't really have them. Well, that's true. Most people don't know about Star Party light control and all of that. So next time, I'll be there next time because I'd like to see that dark sky, and I think it'd be a great place to do a weekend. That would be fun. So we'll see about that. Okay, well, I'm going to stop sharing because unless somebody has something else, I have one other note. Next month's program is going to be visual observing of planetary nebulas. I think it's going to be a really good program. I'm your speaker next month. It's going to be brilliant, as a matter of fact. And the October program is Jim. He's doing a C-Star S50 program. And so we've got two good programs. And then November is going to be on the moon, lunar observing. So we should finish out the year with some really good presentations, and should be interesting and educational. So I'm looking forward to all three of them, especially next month's. It's going to be great. So any other business that we need to get to before we get into the program? No. Okay. All right. I want to introduce Mike Arata. You've seen some presentations from him in the recent past. Mike was an orthopedic surgeon in Fort Wayne for 37 years. He's now retired. During his working years, and I thought this was really fascinating to learn, that you had 3 medical trips to Africa during that period of time. That must have been an adventure. We can.
Good experience and definitely an adventure.
Oh, I don't doubt that at all. And then just before you retired, you went to Tanzania and climbed Mount Kilimanjaro, which I think probably deserves a presentation all by itself. So maybe next year we could get you to, we could have you do that. So yeah, that'd really be an amazing trip. And then we should all read The Snows of Kilimanjaro by Hemingway before we do that. So just to have some context. Mike's astronomy is self-taught. He had a boost from the Purdue Fort Wayne campus here. He did a couple of classes in with the Senior Scholars Program. Then he had a life-changing experience after or during those classes. I'm not sure which, but the life-altering experience was he came to one of our Fort Wayne astronomy meetings, and he actually joined. And then he decided that it was so impressive that he became a board member and then a vice president, and then headed up our program committee. So most of the programs that you've seen over the past, three years or so, 4 years, whatever it is, 3 years, have been a result of Mike and his team beating the bushes for people to do really first-class presentations. At least I like to think so. Once again, Jim, we're not switching to the speaker. How is that? Even though it's on speaker view. Wait, I have Neil on our screen up here. How does that work?
I think you gotta
Is
look.
it only?
I've got you pinned to my screen. I would just click on the Fort Wayne screen where it says FWAS and your logo's there.
Okay.
And,
there we go.
And you can actually pin it
Yeah, I did. I just
Screen. Okay.
good. Thank you.
Yeah.
All right.
Wow. Remote tech support. I can't believe it.
Yeah, live and in person. Zoom works really well. Mike has done presentations for us in the past. The first one was Edwin Hubble, the scientist, the man. That was in 23, and then the ninth planet last year, and both of those were really good. So this year, we're going to hear all about the cosmic microwave background. And so, Mike, I'll turn it over to you.
Well, good evening, everybody. It's good to be back here speaking to you about a subject that I think, if you don't know much about it, I think you'll find it to be a pretty interesting topic tonight. And the topic, as you can see, is the cosmic microwave background. I frequently tonight will refer to that simply as the CMB. So don't be confused if I use CMB frequently, and I will. Okay, so I'll get underway. There were two popular and competing theories in the last century that attempted to explain the origin of the universe. Many cosmologists believed in the steady state or eternal universe. Okay. Steady state or eternal universe. This theory held that the universe had no beginning, had existed forever, and is unchanging over time. Others maintain that a monumental event occurred long ago, the Big Bang, that represented the beginning of the universe when mass, energy, space, and time came into existence. The ongoing debate between these opposing views continued for decades, but the Big Bang theory is now generally accepted by most cosmologists today as the most logical explanation for the creation of the universe. In 1912, Vesto Slifer, a Hoosier native, by the way, working at the Lowell Observatory in Arizona, performed the first measurements of radial velocities of galaxies. He discovered that distant galaxies are redshifting or retreating, thus providing the first empirical evidence for an expanding universe. An expanding universe provided solid evidence that the universe is not static and therefore inconsistent with the steady state theory. Edwin Hubble's groundbreaking work established a relationship between redshift and distance, which provided additional evidence for an expanding universe. His observations showed that galaxies are indeed receding from us and further away, and the further away a galaxy is, the faster it is moving away, a relationship now known as Hubble's law. The expanding universe provided additional proof in support of the Big Bang hypothesis. So knowledge of the Big Bang hypothesis is central to understanding the topic this evening, which is a cosmic microwave background, or CMB. So a brief review of the Big Bang theory should help to better understand the concept. Let's take a few minutes to discuss the important events that are believed to have occurred immediately after the Big Bang. Almost instantly following the Big Bang, a rapidly expanding and unimaginably hot universe was created, about 1 billion degrees Kelvin, or about 1.8 billion degrees Fahrenheit. The extreme heat in this environment created protons and neutrons from subatomic particles such as quarks and gluons. Conditions allowed nuclear fusion to immediately begin, ushering the era of nucleosynthesis. During this very brief period, lasting just several minutes, neutrons began fusing with protons and ultimately created helium. Nuclear fusion and the era of nucleosynthesis then concluded as the universe continued to rapidly expand and cool. At the conclusion of nucleosynthesis, the universe consisted of approximately 75% hydrogen and helium, and 25% helium nuclei, and trace amounts of lithium and other heavy heavier elements. The universe continued to rapidly evolve. The extreme heat in this environment created a plasma state that prevented electrons from bonding. Is there a way I could advance this with the button? This thing's kind of hard to do on the wheel.
Yeah, page down.
Use
Which
the
way?
right button to advance.
The arrow. You don't like the wheel, huh?
I don't like the wheel.
All right, let's try that. How about that?
Okay.
Up and down?
Yeah, up and down. Okay, good. Okay, the early universe continued to rapidly evolve. The extreme heat in this environment created a plasma state that prevented electrons from bonding with hydrogen and helium nuclei to form stable atoms. I'll get it right. There we go. Photons that encountered free electrons, as shown on the left, were repeatedly deflected like ping pong balls. Light was trapped in this dense plasma, which is similar to a thick glowing fog. Over the next 380,000 years, during the era of nuclei, the universe continued to steadily expand and slowly cool to approximately 3,000 degrees, as shown here, Kelvin. Ultimately, this lower temperature allowed free electrons to bind with hydrogen and helium nuclei and form stable atoms. The creation of stable atoms was a monumental event that is termed the epoch of decoupling, for it was during this period that radiation departed company from matter. And so, at decoupling, when the universe cooled to about 3,000 degrees or so, they could form stable atoms, and then photons were no longer blocked from getting out into the universe, streaming into the universe. So the epoch of decoupling is very important to remember. But some also refer to this event as recombination, although technically speaking, protons and neutrons had never previously combined to create atoms. After decoupling, it was as though the cosmic fog had suddenly lifted, the universe became transparent, and for the first time, light was no longer impeded by free electrons and began to stream into the darkness, as shown on the right, on the blue. The passage of this early light has continued unobstructed over the ensuing 13.7 billion years to the present day. This light, however, has greatly redshifted during this time due to the ongoing expansion of the universe. In 1948, Ralph Alpher, along with Robert Herman and their faculty advisor at George Washington University, George Gamow, first suggested that due to cosmologic redshifting, the early light should be detectable today in the microwave portion of the electromagnetic spectrum. This is best illustrated by the next two slides. As light travels through the expanding universe, it is stretched to longer wavelengths, as shown on the right and on the left part of this slide. Alpher and his associates predicted that the universe today should contain feeble microwaves as a remnant of the light that it originally escaped at the moment of decoupling, which would be present in all directions. So in other words, what they're saying, what they believed back in 1948, at the time of decoupling, light streamed into the darkness, and over the last 13.7 years, it is gradually stretched, and today should be detectable in the microwave spectrum. This remnant of light is known today as a cosmic microwave background radiation. Alpers, Herman, and Gamow were unable to spark interest in the scientific community to search for the elusive radiation back in 1948, because at the time there was no widespread consensus among scientists in support of the Big Bang Theory, and therefore no attempt was made to investigate further. Even if they were correct and microwave radiation did exist as they predicted, It was believed to be most likely too faint for detection using the technology that was available at the time. The Bell Telephone Research Lab, which sat atop Crawford Hill in Holmdel, New Jersey, had been conducting work on transatlantic radio transmissions in the early and mid 20th century. Arno Penzias on the left and Robert Wilson on the right were radio astronomers employed at Bell who undertook an investigation to identify the source of background interference in satellite communications. Their work entailed measuring radio emissions from deep space at microwave wavelengths using the large and highly sensitive horn-shaped Holmdel radio antenna, as seen here. In one instance, they employed the radio antenna to make precise measurements of radio emissions from a remnant supernova in the constellation Cassiopeia. They immediately encountered a persistent and annoying background hiss, a little like the background static on an AM radio station. Regardless of where and when they pointed their antenna, this hiss persisted. Never diminishing or intensifying, the weak signal was detectable at any time of the day or night, any day of the year, and in all directions. Unaware that they had detected a signal of great cosmologic significance, Penzias and Wilson investigated many different possibilities that might account for this annoying problem, such as atmospheric storms, interference from ground sources, short circuits in their equipment, even pigeon droppings inside the antenna. They eliminated every possible source, but it made no difference, and the cause of the persistent static remained a mystery. Penzias and Wilson were completely oblivious to the fact that the omnipresent noise was a remnant of the Big Bang, the echo from the early expansion phase of the universe, the cosmic microwave background radiation. This annoying noise would ultimately turn out to provide the most convincing evidence in support of the Big Bang model. Although the existence of the general properties of the cosmic microwave background had been predicted back in 1948 by Alpha, Herman, and Gamow, the scientific community had largely forgotten about it by the 1960s. For that reason, Penzias and Wilson failed to make a link between this annoying background interference and the Big Bang model. However, to their credit, they refused to ignore the mysterious radio noise and continued to discuss it between themselves and among their colleagues. Towards the end of 1964, Penzias attended an astronomy conference in Montreal, at which he casually mentioned the noise problem to Bernard Burke of the Massachusetts Institute of Technology. A couple of months later, Burke telephoned him excitedly. He had received a preliminary draft of a paper describing the work of renowned cosmologists Robert Dicke and James Peebles. And Dicke is in the center, Peebles to your right. And they are cosmologists at Princeton. The paper explained that the Princeton team had been studying the Big Bang model and suggested that all pervasive radiation ought to exist throughout the universe. This radiation today should possess a wavelength of approximately 1 millimeter, putting it squarely in the microwave region of the electromagnetic spectrum. They reasoned that the frequency of this primordial radiation would have redshifted from gamma ray to X-ray to ultraviolet and eventually all the way into the radio range of the electromagnetic spectrum as the universe expanded and cooled over the last 14 billion years. This slide on the left shows that a cosmic blackbody curve, which theoretically derived for the entire universe, beginning with the high intensity gamma rays on the right, 1 second after the Big Bang, followed by the optical 100,000 years later, infrared 10 million years later, and the radio range approximately 14 billion years after the Big Bang. Dickey and Peebles suggested that this red-shifted fossil remnant of the primeval fireball or Big Bang should have a temperature of no more than a few tens of kelvins, peaking in the microwave part of the electromagnetic spectrum at the present time. But they had no idea that they were walking in the 15-year-old footsteps of Alpha, Herman, and Gamma, and they independently and belatedly repostulated the CMB radiation. Suddenly, everything fell into place for Penzias and Wilson. At last, they understood the source of the noise that had plagued their radio telescope and appreciated how highly significant it was. Penzias telephoned Dickey and informed him that they had detected the radiation described in the Princeton paper. Dickey was stunned, particularly because of the timing of Penzias's phone call. It had interrupted a lunchtime meeting which had been arranged to discuss the proposed construction of a CMB radiation detector at Princeton, because Dickey and Peebles had wanted to test their prediction. However, such a detector was now pointless because Penzias and Wilson had already verified the prediction. Dickey put the phone down, turned to his group, and exclaimed, "Boys, we've been scooped." The following day, they visited Penzias and Wilson at the Bell facility, just 32 miles away from Princeton, and inspected the radio telescope and confirmed the data. The race to find the CMB radiation was over, and the Bell Lab team had unwittingly beaten their nearby Princeton rivals. In the summer of 1965, Penzias and Wilson published their results in the Astrophysical Journal, and this was followed by a second article by Dickey and Peebles. The discovery of the CMB radiation appeared to provide the decisive evidence that proved that the universe began billions of years ago and consistent with the Big Bang theory. When Alpha, Herman, and Gamma heard of the so-called discovery of the CMB radiation by the Princeton team, their joy was mixed with some bitterness. They had predicted the echo of the Big Bang long before Dickey and Peebles, but they received virtually no acknowledgement for their pioneering efforts. They were not mentioned in the Astrophysical Journal articles, and neither did their names appear in Dickey's subsequent overview in Scientific American magazine. Nearly every academic and popular article failed to mention Alpha, Herman, and Gamma in the clamor that followed the Penzias and Wilson's discovery. For their discovery, Penzias and Wilson were awarded the Nobel Prize for Physics in 1978. Cosmologists subsequently focused their attention on the only other issue that was problematic with the Big Bang model. It appeared unclear how a universe created by the Big Bang could have evolved to form the structure of our universe today. Many cosmologists suggested that although the early universe appeared to be uniform throughout and the same in every direction on a large scale, or more technically speaking, the early universe appeared to be homogeneous and isotropic, it could not have been perfectly uniform. It is generally believed that radiation and matter were closely connected or strongly coupled until the epoch of decoupling or recombination, when they permanently parted company, allowing light to stream into the darkness. Cosmologists believe that fluctuations in the density of matter corresponded to fluctuations in radiation and temperature, and these features were imprinted in the early universe immediately prior to decoupling. Cosmologic models predict that tiny ripples or baryon acoustic oscillations existed in the plasma, essentially small density enhancements. These ripples would have been greatly amplified subsequently with the ongoing expansion of the universe. The force of gravity would have attracted additional matter, resulting in even denser regions forming that would eventually lead to the creation of galaxy and galaxy clusters. Cosmologists believe that the place to look for the slight variations in density would be to examine the CMB radiation, looking to detect slight variations in wavelength. Radiation arriving from a particular direction with a slightly longer wavelength would indicate that it emerged from a part of the ancient universe that was slightly denser, Radiation from a different direction with a slightly shorter wavelength would conversely indicate it had emerged from the region that was slightly less dense. If astronomers could find these wavelength variations in the CMB radiation, it would confirm the density variations were present in the early universe that would have exceeded the galaxies and made the Big Bang model more compelling. Unfortunately, the CMB radiation appeared to be the same whenever they looked, as shown here on the right. When first detected by Penzias and Wilson, the CMB showed no variation, thus validating and reinforcing the homogeneous and isotropic assumption. Most cosmologists believe that small variations in wavelengths did exist, but were undetectable using the available technology at that time. In the 1970s, the available equipment was only sensitive enough to detect potential differences in the CMB radiation down to 1 part in 100. Another complicating matter was the fact that CMB radiation existed in the microwave region of the electromagnetic spectrum. Extremely small variations appeared to be nearly impossible to detect from the surface of the Earth because moisture in the atmosphere continuously emits weak microwaves that were sufficient to overwhelm the minimal variations in the CMB radiation that were thought to exist. Detectors would need to be placed above the atmosphere to eliminate this interference. Early attempts employed CMB radiation detectors attached to high-altitude helium-filled balloons. They were often fraught with difficulties and eventually abandoned. There was, however, one notable exception, the boomerang balloon experiment that will be discussed shortly. Another effort involved placing radiation detectors in high-altitude U-2 reconnaissance spy airplanes that could remain airborne for extended periods. And that's the U-2 airplane on the right. These efforts also proved to be unsuccessful. Scientists soon realized that their best hope of finding slight variations in the CMB radiation would be to obtain measurements entirely above the Earth's atmosphere, employing a CMB detector mounted on board a satellite. The Cosmic Background Explorer, better known by the acronym COBE, was built in a joint effort with NASA and successfully launched into space in 1989. After 3 years of gathering data, the COBE satellite produced evidence confirming that extremely small differences in the CMB radiation and temperature existed across the universe at the level of 1 part per 100,000. This is a slide that was obtained from COBE. The top image is dominated by an effect known as a dipole caused by the motion of our galaxy relative to the background radiation in the universe at low contrast. In the middle picture, however, the dipole has been removed, leaving the cosmic background emission and the microwave emission from our Milky Way. The emission from our galaxy is the broad horizontal strip in the middle. In the bottom, after removing the microwave emission from the Milky Way galaxy, only the variations in the brightness due to the cosmic background radiation remain. The COBE observations rank alongside the discovery of the cosmic microwave background radiation in terms of their importance to the field of cosmology. The lead investigators of the COBE program were John Mather and George Smoot, that won the 2006 Nobel Prize in Physics for their groundbreaking work. The boomerang experiment consisted of a microwave detector attached to a high-altitude balloon that was launched in Antarctica in 1998 and 2003. It was designed to map smaller portions of the sky and obtain higher resolution images of the CMB. The balloon was carried by the polar vortex winds in a circle around the South Pole at an altitude of 23 miles, returning after 10.5 days, hence the name boomerang. The boomerang study recorded angular diameter distances with high precision. Approximately 1 billion measurements of tiny temperature variations in the CMB were obtained across a wide swath of the sky. From the map of these temperature fluctuations, a power spectrum was derived that registered the strength of these fluctuations or frequencies on different angular scales that contained information and on such characteristics of the universe, such as its geometry and the amount of dark energy in both normal and dark matter. The data also provided strong evidence that the geometry of space is flat, like the surface of a table. The COBE satellite completed its scientific mission in 1993. It was succeeded by the WMAP and the Planck satellite detectors. This is the WMAP. They have both the WMAP and Planck have produced vastly improved images of the CMB radiation confirming and extending the COBE and the boomerang results. The WMAP operated from 2001 to 2009 and measured the CMB radiation at 35 times better resolution than the original COBE satellite. The data from WMAP showed temperature variations of a minuscule 2/10,000ths Kelvin. This anisotropy hinted at density variations where it is believed that matter coalesced into stars and galaxies that eventually formed today's universe. The WMAP data provided information of fundamental significance to cosmology regarding the density of normal and dark matter and the density of dark energy. The Planck satellite was launched by the European Space Agency in 2009 and operated until 2013. It produced the highest resolution yet. Go back, you can see Planck, and then you can see comparing COBE, WMAP, and then Planck, how with the improved technology and higher resolution, how the images improved. Planck measured temperature fluctuations in the CMB with a precision of 2 parts per million at an angular resolution of about 10 minutes of arc, and realized that 60 minutes of arc equal 1 degree. So we're talking less than 1 degree of angular resolution. COBE, for example, measured the angular resolution of 7 degrees. So it went from 7 degrees to just about 1/7 of a degree on the Planck satellite. The colors seen in the Planck all-sky photo represent density variations in the plasma at the time of decoupling, when the universe was 380,000 years old. The red color represents greater density, the blue color less density that existed at the time of decoupling. Density variations are believed to represent the seeds of gravitational formation that led to the creation of galaxies and galaxy clusters in the universe that exist today. The 3D model here was actually taken from the information on the all-sky map by a physicist in Britain, and he published the information for creating this 3D, what you see, this model that I have in my hand. Although I couldn't get it printed with a colorful 3D printer locally, I had a guy I thought was going to do it for me, and then he had it backed out. So I had to paint it myself. So it doesn't have the detail it should have. But what this does, you don't pass it around, it's got the high and the low points on it. And basically, this is an over-exaggeration of the differences in the temperature variations. But it's to illustrate a point, basically, that the higher areas are more dense, the lower areas are less dense. But if it was maybe scale, because the differences are so slight, this would be probably perfectly round. You could tell the differences. Oh, I want to pass this around to Dale. Was kind enough to make a smaller model of the same. So you have two of these tests around. The same idea that is based on the Planck data that you see in this picture here. So in summary, it's now widely accepted that the presence of the cosmic microwave background radiation provides the most convincing evidence to support the Big Bang theory and disprove the steady state model. When we observe the cosmic microwave background radiation today, we look nearly all the way back to the very beginning of the universe, 380,000 years after the Big Bang. Discovery of the CMB radiation by Penzias and Wilson in 1964, followed by the results of Kobe, Boomerang, WMAP, and Planck have led to a much greater understanding of the origin and structure of the universe today and provided insight into how the first stars and galaxies formed, how much normal matter and dark matter exist in the universe, how much dark energy exists in the universe, and lastly, the answer to that, by the way, it's on the right here. The answer is that normal matter only comprises roughly about 5%. That's all useful. Dark matter about 27%. Overabundance of dark energy in the universe. And lastly, the information from the CMB provides evidence about the shape and the curvature of the universe. So that's what we've gleaned from our knowledge of the CMB. I have no more.
All right, thank you, Mike. Any questions for Mike? Thank you very much. Yes. So come back to the microphone, Mike. Can't hear you.
The universe occurs after the decoupling.
You go back.
I'll have the one microphone tonight.
After the Big Bang, immediately gamma rays were present. Okay, and that was very short-lived, long enough to allow for the creation of neutrons and protons, and then nuclear fusion. But that lasted only 3 to 5 minutes, and then for the next 380,000 years, the universe continued to expand and cool. And during that time, as it cooled, the gamma rays immediately were stretched to X-rays and eventually to visible light. At the time of decoupling, probably it was at the point where most of that light that went into space was visible light and infrared light. It had cooled to that point.
So the background radiation is actually caused at the moment of the Big Bang, or shortly thereafter, from the gamma rays that were released at that point.
Well, yeah, they were released, but cosmologists have a theory of inflation, which
Right.
the universe in the early times expanded at such a rapid pace that it expanded and cooled so rapidly that the gamma rays couldn't last long at all. And so as the universe continued to evolve and cool, we had this plasma state that existed, that you had nuclei, and you had photons and electrons that were all sort of trapped in this dense fog, but they couldn't escape because photons would encounter electrons, they kept getting deflected and so forth. And so it took about 380,000 years after the Big Bang, when things had cooled enough, when electrons could bond to form stable atoms, that light would then stream into the darkness, this light that we see today. So it's been traveling unobstructed ever since decoupling. And it's continued to stretch. So visible light, maybe infrared light, but it's continued to stretch and stretch. And now we're down to the microwave wavelength.
So.
Did I answer that okay?
Well, the redshift has been occurring ever since the gamma ray burst at 3 seconds.
Yeah.
Not at 380,000 years.
It's been stretching since the Big Bang. Yeah.
Since, whatever your chart showed there, 3 seconds or something.
Yeah.
Supposedly, during the expansion, we got like 90% of the size of the universe in a billionth of a second or something like that.
It's something unimaginable. Yeah.
Right. Okay.
Yeah.
So
Sure.
the microwave, how did microwave background radiation? That occurred on the time of decoupling, and immediately after that.
No. After it took billions of years to continue to stretch and stretch until finally we got to this point where we are right now at the microwave spectrum.
Is the microwave, are they still being created? What I don't understand is, if something happened more than 14 billion years ago, I would imagine all this stuff on the spectrum. Okay, speed of light is whatever it is, I forget now. Are microwaves about the same? Do they travel around the same speed?
Yeah.
They all travel at the same speed. Yes.
How fast is our local group traveling?
Well,
Because I don't understand why all that stuff hasn't just passed us by.
Because it's streaming.
It would have passed us by a long time ago. So I don't understand why we can still
Because
see.
it's coming from all directions.
Excuse me?
Coming from all directions. It isn't just coming at us. It's coming.
So it's not
It
coming
shows
from, let's say, I know there's no point of the Big Bang, but it's not coming from something like the center of the universe where it started. I mean, okay.
Well, I think if you look at this, for this model to make any sense, we're pictured, we should picture ourselves in the middle of this. And this
In the middle?
radiation is, this is just showing an all sky. In that last picture, the plank should stay over here.
Yeah.
Sorry. Okay, so this is an all sky picture from the Planck satellite. Okay, and so if you look up in the sky, if you were inside here, this is looking out into the universe, you would see this reproduced kind of crudely on this. So the radiation's coming in all directions.
So it's still being produced.
No, it's not being produced, but the universe is still expanding. And so radiation is still being stretched.
It was a flash of light at the instant of creation. And that flash of light being stretched wavelength-wise is what we're seeing. So it's a creation event.
But the flash of light, what is it, 100, what's the speed of light in miles per hour? 186,000 miles per second. Okay, 186, the light is traveling at 186,000 miles per second. Yes. And for sake of argument, our galaxy is traveling at 100,000 miles per second. Light, it's not traveling, I don't know what it is, but light's going to go past it such that we won't be able to see it anymore because it's past where we are.
Yeah.
So then why can we still see it?
Because it's everywhere.
But why hasn't it passed us by?
Because we're moving in space with
But
it.
we're not moving as fast as the light is.
I don't know. I'm not the cosmologist.
I
to
can't,
answer this.
yeah,
I understand the confusion. I just don't know the answer and how to present something.
Okay, I'll ask.
yeah. If you look at this, so this is a dipole. I think our galaxy is traveling towards Leo. I can't remember. It's an incredible speed. So everything is moving in the universe, but the radiation is all pervasive. It's coming from all directions, and it's continued. The universe is continuing to expand.
Is it an echo?
Oh, yeah, okay, yeah, is it an echo?
They call it the echo of the Big Bang.
And what's it bouncing off of?
I don't think they mean it's bouncing off of anything. It's just
No, it's
just from the Big Bang. I don't think it's bouncing off of it. Because it would have to be hitting a boundary and then coming back.
Could some of this be explained because the universe as we know it is expanding faster than the speed of light itself? So therefore would prevent the light from passing us?
Well, there is an edge.
Yeah.
There is an edge that you can't get beyond.
But as far as the question of like the light passing us, if the
I
universe is
think I understand what you're
expanding faster
saying,
than
yeah.
the speed of light, then the light would then pass.
It's a good question. I don't know how fast it's
Again,
expanding.
not a cosmologist.
I don't know.
We need
I
that. We need that.
can't answer that.
Okay, maybe related question. We've all seen the example of the universe expanding, the balloon, and you put marks on the balloon and you blow it up and the marks, get farther and farther apart.
Yeah.
And I've seen that for years and years. But one time, somebody said something about, it's not just marks getting farther apart, but they're not in the middle. Is the universe, because of expansion, essentially hollow? Are we all on the outside? Or were we expanded from the
Oh, yeah,
middle?
it's less dense. It's continuing to be less dense. There's more dark energy than dark matter, and so it's continuing. Cosmologists believe it will continue to expand indefinitely. The universe will continue to do so.
No big crunch.
Well,
Hey,
No.
if I might interject real quickly, I believe the universe is expanding like faster than the speed of light. So the ball we're in, it expands at a certain speed, and that light is given off in between different particles and that became galaxies. But we'd have to read up more on cosmology. If Dr. Zitzer was here, he could probably answer it in a minute or something,
California.
if you look at this slide here too, cosmologists believe that the universe is essentially flat based on this picture. Based on this, because if it is flat, the hotspots would appear to be the actual size that the detector discovered when the boomerang balloon was circumnavigating the Antarctic region. If the shape of the universe was closed, we had more density and energy, and we'd expect to see a picture more like this. And if it was expanding at a much more rapid pace, then you'd see a less dense picture. It would not resemble this at all, as you see in the middle picture. So it's my understanding of why cosmologists believe that the universe is, from our standpoint, is basically geometrically flat. I know it's.
On that note, any other questions? Because I'm not sure we can answer that.
Okay.
So, thank you though. All right.
Okay.
Very good. Well, as promised, I'm going to run us through small groups. Take 5-10 minutes. I'm hoping shorter than longer. And then Laura will give us a concrete example of a small group and the one that she's proposing. So I just want to put the ideas out there on what a small group is and what we might be able to do with them. I just have to find my presentation, which is apparently going to be harder than I'd hoped. I thought I actually had that open. Okay. So now we get to go back here. We get to find it, except I don't want that. I want, where is it? I want that. There it is. Okay. Small groups. Can you plug in there? Excellent. Okay, small groups. Fort Wayne has almost 100 members at this point, and I'm quite sure that within that 100, there's a lot of people that have very similar kind of interests, special interests, whether it's radio astronomy or observing the moon or trying to get your kids more interested in astronomy or any of a particular flavor of astronomy or related. I mean, even if you had an interest in starting into model rocketry, for example, like Julie Kaufman. We have members and you may all have similar interests, and maybe there's 2 or 3 people that would like to together and get into rocketry. Well, we have a lot of resources within Fort Wayne Astronomical that should be able to support all of these individual efforts. So why don't we have people getting together? Why don't we make it easier for people to find other people that have these interests? Why? Well, because people that are more engaged in the club are more likely to be happy with their membership and continue to be members. And if it's directly astronomy related, your skills will grow. And that's part of the idea, is to get everybody to a point where we can actually be growing our astronomical skills so that we enjoy the hobby more. So in order to do that, I think we need to put together something at the board level that facilitates small groups members to find each other. How do you find out who the model rocketry people are? How do you find out who the other parents are that are trying to get their kids interested in it? Well, we have some things that we could do that. So I would like Fort Wayne Astronomy to create the kind of infrastructure that would allow us to do that. Nothing to do with the board, nothing to do with current outreach. It'd just be your interests, and how you take them forward with your group would be up to you, and you do it any way you want. It would be just you and some people that you know or get to know that would be able to do this. So that's kind of hand waving. I agree with that. I've been in other organizations that have had small groups. I think we all have. So why not here? Why not Fort Wayne? So let's see. Some examples of small groups. The Fort Wayne Radio Club. I know we've got a few ham radio people here. In the Fort Wayne Radio group, there is something called the Straight Key Century Club. It's entirely Morse code related. That small group gets together and they have events. They do things independently of the rest of the group. I don't know. There's like 25, 30 people out of the Fort Wayne Radio Club that get together and do this. There's people that enjoy contesting to see how many people you can talk to. There's people that do field day as part of this. All sorts of special interest. And then ARIES, the Emergency Radio Communication Services Group. I think we have someone here that's involved in ARIES. Maybe? No? Yes? Could be. Anyway, there are a lot of people. Storm chasers and other people that report on the weather. All kinds of special interest groups within Fort Wayne Radio Club. And interestingly enough, if you're a member of the Fort Wayne Radio Club, each one of these subgroups submits something to their newsletter, and you find out what they're doing, you find out what their activities are. I mean, you find out all the interests that are there that have more than a few people related to it. Another key group within Fort Wayne Radio Club is their repeater maintenance group. They have a network of radios that you can talk through to other people, and they need maintenance because they live in very difficult environments, and over time things degrade and they need to be fixed. I was a member of the Naperville Astronomy Association, and I wanted to get together with some other people to do visual astronomy. And 3 of us finally got together, and some of the most productive and fun observing I have ever done was with the Naperville Astronomy Association, because one would call another and say, hey, you busy tonight? Can we go out? Can we go out and look at the stars and do some things? And we had some dark sky sites that we had found independently of the club, and we would go out together and do that. So why don't we do that here? Why don't we facilitate the ability of people to get together and explore their groups together? So some examples of small groups that we already have within Fort Wayne is the outreach groups, mainly the Ainsleys. We have a swag group that got together and put together the cups and T-shirts and things that we looked at. There's a solar Saturday group that's trying to get people together that enjoy looking at the sun. There's a group that will be starting up for the muon detector build that we'll hear about later. There's an interest in radio astronomy that could be developed. I know youth astronomy is something that I talk to parents about, and they simply don't have a way to contact each other to find out who they are, who else has kids that we might be able to help. So we have some small groups, but mainly board driven. I'd like to see this pushed down to individual members stepping forward and saying, I'd like to find some observing buddies. How do I do that? So I've already mentioned this stuff. We do have resources, and we'll talk about that in just another minute. We have a lot of physical resources. We have a lot of expertise. I have Pete there looking at me like I'm crazy, but that's okay, because Pete knows about imaging, and he would be one of the experts that I would point other people to in the case of wanting to expand their capabilities in imaging. So what are we going to do? How does this really work? So an organizing member, somebody, an individual member, not a board member, but anyone, has an idea of what they want to do. They want to put together a moon group or a kids group, and they should sketch out what they want to do, because in order to use the resources that we have, they would be talking to a board liaison. And one of the first resources that we would be able to apply to this would be to bringing somebody into a monthly meeting and have the group described. We also put it into the eyepiece. We already have a groups.io site that you could actually today, without any help, without anybody's interference, you could put out a message that says, I want to form a moon group. Who would be interested in getting together with me at the observatory? Contact Laura and we'll figure out how to go forward. Well, we can do that. You could do that now today. You don't need any help. Maybe you need to be reminded that you already have that capability, but we can go further. And as I just said, we have other resources, and those resources would be identified. A muon detector needs some support to build. Maybe you'd like to build it at the observatory. Maybe you'd like to build it somewhere else. But we could talk about all the physical resources that are available and then get this thing kicked off right. So an announcement would be made, again, groups.io, through the eyepiece, through these monthly meetings. Emails. Email would be one of the things that we have that would be very key into getting these groups started. We have 100 members, but not everybody can have access to our membership list. So you'd work through the board to get your announcement email sent out to the membership, and then let people look at that and figure out whether they would like to join based on what you put in your email. So that would get the loop closed, and hopefully you would get a few members based on the ability to contact the people in the club. We could even open it up to the people that are not currently members, our so-called visitors and friends. We could talk about that, see if we could pull in a few more members. So that would get your group started, and then it would be up to the organizer to figure out how to carry it forward and make it successful in whatever way you would define success, since it would be your group. So that's the idea. The features: groups run by members, board members as a liaison for all the physical resources that the club has. If you needed to use like the observatory, the inside of the observatory, you would need a key holder. Most board members are key holders. If you only wanted to use the grounds, like you wanted to shoot model rockets, you have access as a club member to the observatory grounds 24 hours a day, 7 days a week. You don't need permission to go out there. You can just go out there, fly your kites, shoot your rockets, set up your telescope. It's all the same. So a group of one is also okay. You have to start somewhere, right? So Laura would be the organizing member of the moon observing group. So right now there's technically one member, maybe two, maybe only one. So anyway, so what are the resources that we have? We have expertise in a lot of different areas, a lot of observing expertise, imaging, radio astronomy, all sorts of things. We have the email list. We have a meeting place, the StarQuest Observatory. We could even loan the Zoom a Zoom link for you, so you could meet if you needed to via Zoom. At least I think we can. As I've mentioned a few times, the observatory grounds. We have our media sites, social media sites, Facebook webpage, groups.io, IP space. I mean, if you had a group and you wanted it to grow, you might want to actually put out pictures and text about what you did over the past month and put that in the eyepiece. You wouldn't have to do that. It's your group. You could do it any way you'd like. But if you would like to have a few more members, giving it some visibility might be a good way to do it. We have telescopes. We have a library. We have a 3D printer, maybe two, at least one, and we could make that available. And if you had ideas that required some funding, we could talk about how the board could assist you in creating a funding mechanism for your group. Not necessarily Fort Wayne Astronomical as a whole, but if it really benefited the Fort Wayne astronomy as a whole, we could talk about that too. We're not the Bank of Fort Wayne. We don't have a great deal of assets for it, but we have some. So we could talk about that. And I put it at the bottom for that reason. We're not the funding source of first resort. So a lot of resources. We just need the membership to figure out and carry forward on their observing needs and desires. So that's my thoughts. So create policies. Our next steps are create policies that define how the groups would operate. That's been done. There's a page in the eyepiece this month identifying the small groups that we do have and the new ones that are coming. And publicizing at monthly meetings. We're going to do that starting this month, starting with Laura. And I've had an inquiry about putting together a radio astronomy group, and we'll be hearing about that next month. Joe Lawrence wants to do that, and we'll get some time next month. So I've taken more than my 10 minutes. So that's actually all I had. So let's move on to Laura. Well, if you want your group, I think you would. Right? So we need to find your drive. Which one is it?
Should be Lexar.
Lexar.
Yeah.
And you want to go find it? I don't have to.
Yes. So let me see.
Jim, you can cut this part out too when you're putting video together.
There we go. Okay.
And then, yes, sir.
Let's say I wanted to form a group.
Sure.
and I don't have a list of all the members,
You don't, we do.
but I have the email that you or somebody sent out saying we're having this meeting. And that email probably went to all the members. So I hit reply all and say, I want to form a group. Would that go to all the members?
Gosh, I hope not. I hope we're using the blind carbon copy feature of the email. We really need to protect our membership
I don't see
for
all the
privacy.
members.
And that,
But your message goes to all the members, so if I reply all of that, go to all the members.
you could try it, but if we use the blind copy feature, I don't think that should not work. That should not work. Have you got your, right here. Okay. Right. That's it.
All right.
And then we need to
Yeah.
go back to, really. There we go.
There was a blank one at the beginning.
Yeah. And then we need to do this. And then we need to go here, and then we need to pick up this. And then it's all yours.
All right. Okay. What's your moon story? I know everybody's got one. I mean, you don't even have to be an amateur astronomer to have a moon story. Everybody's got one. Everybody's got at least one. Anyway, my moon story, as far as the FWAS is concerned, is I had a moon group 30 years ago with this club. And, well, Russell came along and we kind of got out of the group, and that was apparently kind of the end of it. So what my thought was when we first started talking, when I started hearing about small groups, I thought we need to start up the moon group again. So, okay, fine. What are we going to do? Anyway, go on. There's all sorts of things you can look at. Moon jigsaw puzzles for cloudy nights. This is incidentally the astronomy puzzle of the day, which sometimes they link it to the astronomy picture of the day. It's they're pretty cool, actually. Name that phase for, like your kids or people that don't know anything much about the moon yet. Lunar occultations. This is the fun part for me. This is one of the fun parts for me. More lunar occultations. Other things that are related to the moon. This particular plant I shot in my garden years ago. Some people will know it as money plant. It's named for its resemblance of its seed pods to a gibbous moon, just like this thing. Or you can just be looking at the regular moon. Lunar eclipses would be an obvious thing that moon group people would be interested in. Next one's next March. I love the Marius Hills, or this whole area is one of my favorite areas on the moon. And you can talk about libration, which is why you don't have exactly 50% of the moon that you can see. It's 59%. That other 9% is just on the edges, but still it brings some things that would normally be on the edge further into view, and you can see them better. Very cool. Okay, the harvest moon effect, which is one of the things I learned about real quick when I was doing deep sky observing was there isn't really a lot of deep sky observing in August because of the harvest moon effect. Grouping of then I discovered just this past year that where the harvest moon rises at the same time every night approximately. Easter this year, I had the interesting experience. I saw the moon set about the same time 3 nights running because I work at a weird hour. I called it the Paschal moon effect, but anyway. Or you can just be looking at mountain ranges and really cool craters. Anyway, we're talking about launching a moon observers group, as we've mentioned, this fall. I'm thinking, we haven't really decided yet, but I think probably the most sensible time to get started is Saturday night, October the 4th is International Observe the Moon Night. Saturday night, October 4th. So, you know, we can get together at the observatory. If we can Zoom that, that would be awesome, because some people will be doing that. This International Observe the Moon Night is a NASA thing, so you can join together with other people connected with NASA, and it's really cool. And incidentally, if anybody's got a better name than the Moon Observers Group, hey, speak up. I'd love to hear it. We talked about one of the things we talked about was we could go through the Astronomical League moon observing program and get those badges. That won't take us very long in my experience. From what I'm seeing, you just got to focus on it. But if that's not something you're interested in, well, you don't have to do it.
I can support that because I've done that.
Yeah, exactly. And I know there's at least one person that's working on their moon badge right now. So we'll see.
I'm
Yeah.
too short. I couldn't catch the crescent, the waning crescent tonight. It was too far.
Oh, yeah. Well, shoot. And that's annoying because that's the first thing I've gotten. I haven't got a lot of other things, but that was my first target because of when I work. So anyway, you can we'll be continuing to talk about it as the next month or so goes by, month and a half thereabouts. So we'll be in contact. We'll talk to you later. Bye.
Would you go to winter time, or would you end observing if observatory closes?
I would personally, I would be open to doing some lunar observing in the winter. Not a lot, not all the time, but you know.
We just draw the line at 10 below or something.
Oh, certainly, we're going to draw the line at 10 below.
25 is my plus 25 is my time.
Well, yeah.
Is this strictly tied to the outreach efforts, or is this independent of the outreach efforts?
I would say it's independent of outreach efforts because, I mean, the first thing I did with this particular group was I was curious about, there is a rill basically in the very center of the moon called the Ariadius Rill. And it's essentially east and west. And I was trying to figure out why I had never seen this thing, in spite of the fact that it's right smack in the middle, and it's big, and it's visible on. It should be visible on a first quarter moon. What first quarter moon? So why is it on this map and I've never seen it before? It turns out libration has an effect on whether it's visible or not.
So you could send out like emails on the night before observing.
Sure.
It would just be people interested in lunar observing that sign up for those kinds of emails to get together. It could even be virtual, as you mentioned.
Exactly.
Zooming people out. The moon is a good thing for a light polluted sky.
Yes.
It's easy to find.
Mm-hmm.
So there's a lot of, and it's a great object to start with. So I would think that people of all ages would be interested in getting into this.
I agree. And
send out the email to groups.io to solicit.
Yes. At least to begin with.
Yeah.
Since I am with groups.io at this point, I can.
About half our members are.
Good.
We need more SAMs. We need the approval process figured out now that Phil is no longer doing that. But the other thing is, you have a board liaison to get access to the email list. So
right.
You have kind of an advantage.
This is true.
So anyway. Okay. Any other questions for Laura? Right. Any other questions about details of groups? I mean, it is something that you could do automatically now. It's just whether or not you realize you can do that. As I said, there's no reason that you couldn't pull together a group by groups.io or just coming to one of the board members, me, somebody, and saying, I'd like to send out a email to the entire membership to get this thing going. It's really the minimal part that you need, is just to get the word out that you're trying to start something, and then to describe how you think it might have operated first, and then go from there. So anyway, you'll be hearing more. It'll be in the IPs. We'll have some additional information and groups forming up. So hopefully we'll get some momentum on this. I think it should be really fun for the membership to realize the potential that we have here and get it going. Because it's something that we can't. It's not a top-down effort. It really needs to be a bottom-up, because you can't force people to participate in something they don't want. So this is something that only a handful of people need to do. So think about it. It's up to everybody to carry this forward if you have interest in doing something like that. So anyway, so that's about it on small groups. So anyway, Mike, thank you again. Again, next month we have me next month doing planetary nebulas. So look forward to doing that, and we'll see you in September. Or lose you to a summer love, I think is how that goes. Thanks, everybody. Thanks for coming out.